Hello everyone, I am Sixun Huang from National Kaohsiung University of Science and Technology, Taiwan. The topic we introduce is how to write a PyTorch program for machine learning. In order to focus on why PyTorch makes machine learning programming easier and more intuitive, we stick with a simple and familiar problem, a linear regression with a single feature. The outline of this lecture includes introduction about the description of machine learning, the basic programming paradigm for machine learning, and the supports from PyTorch, linear regression about its problem description, gradient descent algorithm for finding a good solution, and a program implementing gradient descent algorithm using NumPy package. PyTorch programming about how to rewrite NumPy program by introducing PyTorch AutoGrad and optimizer packages, data providing, and model building mechanisms. Traditional programming for machine learning is to call the rules by the programmer. The rules is used for producing output by predictor program. For obtaining accurate results, the rules are generally obtained by consulting domain experts. Instead of coding rules by the programmer, ML is to learn the rules from training data. Rules are the relations between the input and output. In other words, the role of the programmer is replaced by a training program, and the expert is replaced by training data. The rules are generally referred to as a model, and the stage to generate the model is called the learning stage. Here shows the basic learning paradigm used in the area of machine learning. Step 1 is to randomly initialize the model to be trained. Step 2 is to repeatedly visit all data items in the training data set, consisting of capital M items for n times. In ML terminology, visiting all items one time is called an epoch. For each iteration, we firstly shuffle the data items, and then sequentially load little m to update the model. The m data items used for one update is referred to as a mini patch. For example, we have a data set consisting of 6 data items. During learning stage, we randomly initialize the model denoted as C.0. At the first epoch, the data items are shuffled and then divided into 3 mini patches, each of which have 2 data items. Then, each mini patch is loaded and used to update the model, and totally, we have 3 updates for the first epoch. We do the same thing for the second and the third epochs. Next, we introduce the supports from PyTorch for writing program to implement this basic learning paradigm. PyTorch was developed by Facebook and is a machine learning package for Python language. The main supports from PyTorch are dataset management and exploring, model building, optimization utilities, and parallel processing by using GPU. For dataset management and exploring, Dart data subpackage contains dataset and loaders to make data processing easier. Dart NN subpackage contains modules and extensible classes for building ML model. Dart AutoGrad subpackage provides differential operation, and Dart optimizer subpackage contains standard optimization operations. Torch package contains library for the defined tensor data type to use GPU. Next, we focus on a linear regression problem to introduce why PyTorch makes machine learning programming easier and more intuitive. The linear regression problem can be described as follows. Given n data points sampling from a linear model, y equal to a times s plus b. The objective is to find the model parameters a tilde, b tilde that most fits these points. That is minimizing the fitting error. For example, given these 6 points, we find a slope a and intercept b to fit these points as possible as we can. Mean square error or coded loss is the general way for measuring the fitting error for linear regression. It evaluates the fitness of model parameters AB as the average of square error between ground truth yi and the predicted value y hat I using AV. For an example with A and B both equal to 1.0, we list the predicted value y hat I for all Si as this table. Next, we compute the all predicted errors. This equation here is the MSE loss of A and B both equal to 1.0. Thus, the solution denoted as A tilde B tilde to linear regression is the parameters that minimize MSE loss. In other words, we explore over A and B parameter space so as to find the parameter values with minimal MSE loss. Here, we introduce an algorithm called the gradient descent to minimize MSE loss in an iterative manner. Since the gradient of the minimal point is 0, gradient descent algorithm starts from a randomly selected point A0, B0, and moves toward the minimal point by gradually decreasing the gradient. At each iteration, we take a step proportional to the negative direction of gradient. Negative gradient means move forward by increasing the parameter values and vice versa. Large gradient means it is far from the minimal point and we should take a big step and vice versa. Let A and B sub t plus 1 be the parameter values of A and B at time t plus 1 respectively, and they are equal to AT and BT plus the displacements delta AT and delta BT. According to the above description, delta AT and delta BT are proportional to the negative direction of gradient with respect to A and B. By introducing a constant eta, coded learning rate, the update of A and B from time t to time t plus 1 can be expressed as these two equations. Here, we compute a partial derivative with respect to A. Since partial derivative over summation is the same as summation over partial derivative, we can obtain this equation. This equation is obtained by applying chain rule. The partial derivative with respect to A of this term is equal to minus Si. After simple calculation, we obtain this equation. Similarly, we compute a partial derivative with respect to B and obtain the final equation after simple calculation. The derived equations are used to substitute for these two terms. Thus, we have the equations for updating A and B respectively. This term is the predicted value at time t using the parameters at and bt. The pseudocode for linear regression based on aforementioned basic learning paradigm is listed below. Step 1 is to randomly set AB as A0, B0. At each iteration, we firstly shuffle the data points and divide them into mini batches. After that, we take each mini batch to update A and B. The update step consists of the 3 sub-steps, including computing MSE loss, computing partial derivatives with respect to A and B respectively, and updating A and B by adding displacements proportional to the negative derivative of gradients. Firstly, we use NumPy package to implement gradient descent algorithm for linear regression. We begin with importing NumPy package, initializing data points as a 6x2 NumPy array, and setting the hyperparameters, including number of epochs, batch size, and learning rate. At step 1, we randomly initialize A and B using random method in NumPy random package. At step 2, we repeatedly visit all items in the variable data points for several times. At each time, we shuffle the items by shuffle method, and then sequentially take a mini batch to update A and B. Here, the codes for updating A and B directly implement the aforementioned equations. They are computing the MSE loss, partial derivatives with respect to A and B respectively, and updating A and B by adding displacements. However, when there are many parameters to be estimated, it is hard to compute their gradients and to update them respectively. To release the burden of computing partial derivatives, PyTorch provides AutoGrad subpackage, including differential operations on PyTorch tensors. By using the AutoGrad subpackage, you should define model parameters as PyTorch tensors. Convert the data for updating model parameters to PyTorch tensors, and perform backward propagation via calling backward method of those tensor variables. Accordingly, we firstly modify the NumPy code for linear regression to define A and B as PyTorch tensors. Then, the data for updating A and B is converted to PyTorch tensors. Finally, instead of directly implementing aforementioned equation, we compute partial derivatives with respect to A and B by performing backward propagation via calling backward method of the variable MSE loss. The code after modification to compute partial derivatives by using AutoGrad subpackage is shown here. We highlight the 3 modified parts by green rectangular boxes. To update model parameters in an easy way, Torch Optimizer subpackage that implements various optimization algorithms can be used. The first step to use Optimizer subpackage is to create an optimizer object by taking model parameters and the learning rate as arguments. Then, we update the model parameters by invoking step method of the created optimizer object. Since gradients are accumulated in PyTorch, we zero the gradients of all variables by invoking ZeroGrad after updating. As mentioned, we create an object called the optimizer by taking A and B and the learning rate eta as arguments. The update to all model parameters is performed by calling step method of the optimizer. Finally, we zero all gradients by zero grade method. The code after modification to update model parameters by using optimizer subpackage is shown here. As before, we highlight the modified parts by green rectangular boxes. Instead of defining the data points for linear regression as a single variable, we will talk about how to represent the data in a more extensible and modularized ways. In PyTorch, providing data are based on three classes in utilities.data package. A dataset is represented by an object of dataset class that has the interface to index data items. That is, a dataset is considered as a Python list of tuples. The object of subset random sampler class shuffles item indices. In this example, it randomly shuffles the item indices ranging from 0 to 5. The object of data loader class slices the dataset according to the desired mini batch size. With mini batch size equal to 2, the dataset is divided into 3 mini batches for further iterating. We firstly declare a class inheriting from dataset abstract class to represent a dataset, and then implement its 3 abstract methods. INIT method is a constructor to take arguments needed to build a list of tuples. GetItem method receives an index and returns a data item at index position. LEM method simply returns the number of items in the dataset. After declaring a dataset class, we create a dataset object. Create a subset random sampler object by taking the list of item indices as argument, and create a data loader object. The creation of the data loader object takes the created dataset object, subset random sampler object, and the mini batch size as arguments. Accordingly, we declare a class called the LR dataset, inheriting from dataset class, and implement 3 abstract methods. INIT takes the points for linear regression as input, and stores them to instance variable .data points. GetItem method returns the tuple xy at index position as PyTorch tensors. LEM method returns the number of data points by LEM method. After that, we create a dataset object as LR underline dataset, and then generate a list of item indices for creating a subset random sampler object as sampler. The LR underline dataset, sampler, and the batch size are taken as arguments to create a data loader object as LR underline loader. Having a data loader object in hand, the NumPy code for shuffling and mini batch iteration can be replaced by a simple for statement. Here shows the modified code after using 3 PyTorch data providing classes. Furthermore, we also declare a class inheriting from module abstract class to represent a model, and implements its two abstract methods. INIT constructor defines the model to be learned. Forward method receives an input S and outputs the prediction. In PyTorch, you should not call forward method directly, but the whole model itself. Accordingly, we declare a class called the LR model inheriting from module class and implement INIT and forward methods. In INIT constructor, we initialize base class by passing class name LR model as argument and create two objects of parameter class for model parameters A and B respectively. The required grade flag are set to true to indicate that the computation of gradient is required. For forward method, it returns the prediction A times X plus B. After declaration of LR model class, we create an object called the LR underline model of this type. By encapsulating the model in this way, we can remove these two statements for defining model parameters. The parameters to be updated by the optimizer object becomes invoking parameter method of LR model object to retrieve the model parameters. Instead of coding directly, the prediction Y header results from calling forward method in training mode. Here shows the modified code after model building by using module class. The complete code using PyTorch for linear regression is shown here. It includes importing required packages, the declaration of LR dataset and LR model classes, setting hyperparameters, defining objects for data providing, defining model and optimizer, and running learning paradigm. In this lecture, we introduce the use of PyTorch for facilitating the development of machine learning algorithms. We introduce basic learning paradigm in machine learning and give the NumPy implementation for linear regression. To improve the NumPy program by PyTorch, we introduce the AutoGrade for computing the gradients with respect to all model parameters and the optimizer for updating model parameters. Next, we describe about the three classes, including dataset, subset random sampler, and data loader for data providing, and the module class for model building. Thanks for your listening and have a nice day.